All right, friends, welcome back. So, when we were talking last time, we were working through the synthesis of limonene, which is from citrus oil, from geranyl pyrophosphate, the linear precursor. And we had talked about the four basic toolbox, the three items in our toolbox for terpene mechanisms: leaving group leaves, nucleophile attacks carbocation, leaving group leaves again, and then pi bond attacks carbocation to make a new bond between gold 4 and red 5. And we had pointed out that this follows Markovnikov regioselectivity, which puts the positive charge on the more substituted carbon. Then lastly, elimination of a beta proton gives you limonene, and that's how we got to the natural product. We talked about how it's important to be able to look at an isoprene or a terpene product, identify the isoprene units, and then know which bonds came from the linear precursor, that's in red, versus which bonds came from the reaction that generated this molecule. If you can identify the ones that were present in the linear precursor, you don't need to worry about those anymore because you already made those. Your mechanism doesn't need to explain that. It's the blue one that you have to be able to explain, and that can help you narrow into what kinds of steps you need to do in the mechanism. So today we want to show you how you can get a lot of different and interesting natural products through these few steps that we've identified. So from this same precursor, which I will copy and then I'm going to erase some of the stuff. Oops, somehow, didn't want that. Copy, paste. From that same precursor, we can get the following natural product. Which is kind of weird looking. It's got a carbon here bonded to two methyl groups, and that carbon is also bonded to two carbons within the 6-membered ring. You could think of this as a 6-membered ring that has a carbon hanging out below it, sort of like a tent. And if you wanted to draw this from a different perspective to give you a different idea of what this molecule might look like, this would be one way to do it. You sort of have a 6-membered ring here and then a 4-membered ring there, and the two rings share two sides. This natural product is called alpha pinene. It's an alkene hydrocarbon nonpolar molecule that you can isolate from the oil of a pine tree. And it's available from this precursor. So let's see if we can identify the isoprene units in alpha pinene. And again, anytime you do this, you focus on first the dimethyl tail, because if you can do that, then the carbon that's bonded to two methyl groups is carbon 2 of an isoprene unit. And the methyl groups are carbons 1 and 3 respectively. The other thing you do is you focus on the branching methyl groups. The methyl group will be carbon 3, and the carbon that it's bonded to will be carbon 2. And then you have to do your best to stitch things together in a reasonable way with bonds between 5 of one isoprene unit and 1 of another. And sort of following the way we did things in the precursor to the left, it maybe makes sense to have the isoprene units be assigned this way. Okay, and then this bond in red is the one between gold 5 and red 1 that was present in the linear precursor, geranyl pyrophosphate. And then the bond that I'm going to highlight in blue, the bond between gold 4 and red 5, is the bond that we made when making this carbocation. So now we just have to explain the remaining bond, which is this one that I'm just going to highlight in light purple. That bond between gold 2 and red 4 is the one we have to explain. So anytime you're asked to propose a mechanism for a terpene synthesis, you should always start by figuring out what bonds you have to explain. That narrows down the possibilities. Okay? All right, so any ideas? We want to make a new bond between gold 2 and red 4. What are you going to do? Go ahead.
The double bond is going to attack the carbocation.
Yeah, is the double bond just going to attack the carbocation? Yeah, that's reasonable. We need a bond between red 4 and gold 2. We have a nucleophile involving red 4. It's the pi bond. And remember that that pi bond is actually, from our perspective, both above the plane of the page and below the plane of the page with electron density. Also remember something, you may not remember, something I said last time. The stereochemistry of gold 4 is set in a previous reaction. The enzyme, which is chiral, favors the dash configuration here at gold 4. So this isopropyl group with the carbocation on gold 2 is pointed downward into the page, and it's possible for the pi bond between red 2 and red 4 to attack carbon 2, gold 2. As you do that, does it make sense why does it make sense that we form a new bond between red 4 and gold 2 instead of red 2 and gold 2? Is that, yeah, go ahead.
Because then the positive charge can be on more substituted carbon.
Great, yep, so that positive charge can be on the more substituted carbon. We call that, from 351, the Markovnikov rule. I found when drawing out terpene mechanisms that it's helpful to me, at least, to draw things after I make a new bond that's going to make the molecule more complicated. The next drawing I make is kind of distorted and has unrealistic bond lengths, but it at least gets me correct connectivity, and then I can redraw later to get things right. So if you remember, we just made a new bond between 4 and 5. So I'm going to draw we made a new bond between red 4 and gold 2. So I'm going to draw that new bond like this. And it looks ugly and it's too long, but it communicates the right idea that after this reaction step, red 4 is bonded to gold 2, and I need a positive formal charge on carbon 2. At that point, if I want to redraw the molecule to make it look more physically reasonable, I can. That's going to have gold 2 actually hovering under the 6-membered ring. As I told the 9 a.m. class, the season of student evaluations of faculty performance are upon us. So if you want to report to BYU just exactly how much time I waste on coloring, you can do that. I'm sure they will be very interested. Okay, so you get this carbocation. Now, how do we get to alpha pinene? Base eliminates the beta proton. Now, if you look at it, there are a couple of beta protons that can be acidic. At 9, somebody asked, as you can see, to get alpha pinene, a base is going to remove this beta proton and give you this alkene. It turns out that if you remove the other beta proton on the methyl group, you can get an isomer of alpha pinene, which exists too and is also a component of pine oil. It's called beta pinene. But somebody asked, well, why don't I remove the proton on 4? That would give me a tetrasubstituted alkene. And the reason is it's kind of complicated and not actually obvious from this structure. You remember that a p orbital, that a positively charged carbon has an empty p orbital on it, right? And that p orbital is above and below the plane of the page. In order to be removed by a base, the proton that is beta to the positive charge must be able to line up with that empty p orbital. This proton can, whether it's a dash or a wedge, because again, that p orbital is both above and below the plane of the page. This proton can, just by rotating around this carbon-carbon bond. This one, if you built a model, you would see is going to be held perpendicular to the p orbital on carbon 2. So it's not going to be very acidic. A base can't remove it. And the other explanation is, in terms of this ring system, a double bond really would not fit very well there. It's hard to make. Okay, so 2 new complicated natural products that come from a precursor that made a simpler product. Now you might ask, how does a pine tree know to make alpha pinene instead of citrus oil? And how does citrus know to make limonene instead of alpha pinene? My answer is, I don't know, but it has to do with the enzymes that catalyze the reaction. And oh, it must be the enzyme is our hand-wavy explanation for things in this class. Though, I mean, it's really true in the sense that biology has a lot of enzymes that do a lot of things, and you can control outcomes through regulation of reactions, and you'll learn more about that in biochem. Okay, questions about alpha pinene? Yeah. Is beta pinene just a different chair conformation? It has the double bond in a different place, so you would just draw it there. Other than that, I guess, so do they have different conformational properties? I don't know. They might have slightly different boiling points and whatnot. I don't know whether they smell different or not. It's kind of interesting. A lot of these terpenes have characteristic smells. Okay, let's see, what else? All right, let's do another one that also comes from this same linear precursor. This one is fun because, I'm sorry, from the same, not linear precursor, but from the same starting material, the same carbocationic intermediate. I like this one because of its shape. Because to me, it looks like a duck. You guys were what, like 4 when that dropped in 2008 or something like that? I can't remember when that was, but you know about the grape. You know about the duck, okay. So, let's see if we can identify the isoprene. This is actually called alpha-thugene. Unfortunately, it is not present in duck oil. That would have been awesome. I don't know what oil of duck is, but it actually comes from rosemary and some other herbs. So see if we can find the isoprene units here. Again, start with the dimethyl tail. So that means this is 1, 2, and 3. That means this one's 4. If you're sort of following the pattern that we've done before with limonene and alpha pinene, it makes sense to call this 5. That lets this be 1, 2, 3, 4, and 5. So we'll go ahead and highlight all of those, and then let's try to get another sense of which bonds were present in the linear precursor and in the cyclic carbocation, and which new bond we have to explain. So always the bonds between 5 of one isoprene unit and 1 of another were present in the linear precursor. Then we have this blue bond between gold 4 and red 5 that was also present in the carbocation. That means the only one we have to explain is this one between gold 4 and red 4. Okay? Now, let's come up with a mechanistic hypothesis. We want to make a new bond between red 4 and gold 4, and indeed we have a nucleophile involving red 4, so you could imagine the pi bond attacking something and the new bond going to 4 so that the positive charge could be on more substituted 2. But the problem is the electrophile's on the wrong carbon. The electrophile's on carbon 2. We need it on carbon 4. Any ideas? Hydride shift, yes, the evil specter of carbocation rearrangement returns, just like Palpatine, inexplicably. Palpatine returned. Boo, some of you don't like that. I was okay with it. They retconned it pretty well. I mean, the whole Bad Batch thing was sort of about explaining where Palpatine came from. I'm easily derailed. Where were we? Carbocation rearrangement. So this is the fourth element in our toolbox for terpene chemistry, carbocation rearrangement. This can be either a 1,2 hydride shift or a 1,2 methyl shift, or it can even be a 1,2 alkyl shift. You'll see 1,2 alkyl shifts that allow ring sizes to change in terpene chemistry. Now, just to review briefly, in 351, you were taught that carbocation rearrangements can happen when a secondary carbocation is adjacent to a tertiary or quaternary carbon such that a 1,2 methyl or 1,2 hydride shift would generate a more stable tertiary carbocation. Sound familiar? That's sort of when you were expected to predict that this would happen. What happens in a 1,2 hydride shift is that if we imagine this carbocation with a positive charge on this carbon, signaling that there is an empty p orbital on the positively charged carbon, the proton that's beta to that positive charge is already hyperconjugating with it, sharing its electron density. And so it's not such a stretch to imagine that hydrogen leaning over with its electrons to dump them into the empty p orbital. That would turn, and then the hydrogen that shifted over would now be bonded to this second carbon. And now the carbon on the left is going to be positively charged with an empty p orbital on it. And this can actually go both ways. In the structure that I've drawn here, you have a tertiary carbon adjacent to a tertiary carbocation. That's different from what we did in 351. In 351, you always, when you were asked to predict carbocation rearrangements, in general, you were dealing with a tertiary carbon adjacent to a secondary carbon. We limited that so that you wouldn't be confused because, frankly, carbocation rearrangements are messy, but nature is not so constrained. In nature, it's totally fine to rearrange a tertiary carbocation to a different tertiary carbocation. They're similar in stability, so you would predict the equilibrium constant would be close to 1 anyway. So in terpene chemistry, you sometimes have to do carbocation rearrangements to get the positive charge in the right place to do the next step. And when you do, tertiary to tertiary rearrangements are just fine. Now, I'm still not going to ask you to predict that, but if you see in a terpene that it's necessary, you should be able to know that it did happen. Does that sort of make sense? Okay. Right, so here we need, the carbocation is on tertiary gold 2. We need it to be on gold 4 so that the positive charge can be in the right place for nucleophilic attack to make alpha thugene. So this is how we would show the 1,2 hydride shift. Remember, that just indicates that the proton is leaning over. In so doing, stereochemistry is preserved, by the way. The stereochemistry actually isn't going to matter in this case because the proton goes on to a carbon that's not a stereocenter, but you would see in general, if it were, that the hydride or the methyl group that shifts over stays on the same side of the molecule that it was on originally. So now we'll put a positive charge here. There is the hydrogen that shifted over. Just going to number things again. Oh, I did it wrong, didn't I? 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. Now we're in the ideal position to attack from the pi bond between 2 and 4 to attack gold 4. That's going to make a new bond. And again, it's probably useful to, at first at least, draw the molecule in exactly the same way, but draw the new bond in sort of a extended, weird way that gives you an idea of the connectivity without asking you at the same time to try to make the molecule look pretty. So there's our new bond in purple, and there's the positive charge on carbon 2. If you want, you can redraw that to be something that looks a little neater and presents more reasonable 5 and or 3-membered rings, something like this. And that looks a little bit more like a duck. And then, finally, the last step, as you can see, is going to be elimination of a beta proton to give us alpha thugene. Okay? All right, so how does this show up on a test? Well, there are a couple of ways. First, in terms of mechanism, I could show you a starting material. In this case, it might be geranyl pyrophosphate, and a product, alpha thugene. And then I'll show you mechanistic steps that lead, that are potential mechanistic steps involved in conversion of geranyl pyrophosphate to alpha thugene. And in one format of the question, I might show you all steps that are totally reasonable, but some of them don't lead to the right product. For example, if I wanted you to get to alpha thugene, a step that doesn't lead to the right product might be if I had a proton on this beta carbon and showed a base removing that proton. Does that sort of make sense? You'd look at that and be like, oh, that looks reasonable, but it doesn't lead to the right connectivity. Or I might show you this step, which is also reasonable, but leads to alpha pinene, not alpha thugene. It gives you the wrong connectivity. Or I might show you this step that leads, that's the elimination step that leads to limonene. So one format of terpene questions is to give you reasonable mechanistic steps, but only some of them lead to the desired product. So you got to be smart and follow the connectivity. Go ahead.
Should we memorize like the structures with these names, or will you give us the structure?
No, you shouldn't memorize the structure and the name. You can if you want, but I would, in a mechanism question, I always give you the structure. Yeah. Another format might be to give you just all steps that are on the pathway, but some of them are just wrong. Maybe the arrows are going in the wrong direction. Maybe the structure of the intermediate is wrong. Okay. A second way that we can ask questions about terpenes is to focus on identifying isoprene units and to focus on which bonds in a terpene product were present in the linear precursor versus which ones were not. So let me give you an example of this that's kind of complicated. You've already worked with monoterpenes where identifying the two isoprene units is pretty clear. You've had some practice on that. I'm now going to draw a horrible, complicated natural product. I'm first drawing its linear precursor. This linear precursor is called farnesyl pyrophosphate. I'm missing the double bonds yet. I'm putting them in just a second. And here are the isoprene units. We'll start with gold, and then we'll go with red, and then blue, because we're sticking with call signs of Star Wars. Of Star Wars wings. Let's see, and then here is the product. Prepare yourself. It's horrible. Not done yet. Now we're done. This is called cedarol, and it's from an essential oil, component of essential oil from cedar trees. Okay, so I want you to take a few minutes, 2 minutes, 3 minutes, and see if you can identify the isoprene units that are present in this molecule. Once we've done that, we'll go through and identify which bonds were present in the linear precursor versus which bonds had to have been made when you made cedarol. So go ahead and take a few minutes. I'm not going to help, I'm just going to stand here, and then we'll reconvene. See what you can come up with. Sorry, I'm just watching Clone Wars while you guys. Duchess Satine is in prison, so okay, I'm distracted. That is a sad one. Season 5 is really sad. It's like it's going to be spoiler alert. Okay, back to work. Sorry. All right, now maybe take a minute to confer with a neighbor, see what you think, revise your hypothesis, and then in 30 seconds I'm going to ask one of you to use the Apple Pencil to draw your isoprene units up here, okay? Unlimited power. Volunteers. Any volunteers distribute? Go ahead. May the odds be ever in your favor. So just to get you oriented, what's your name?
I'm Hank.
Hank. Hank is brave. Let's give Hank a round of applause. Okay, Hank, so this is a pen, this is a highlighter, that's an eraser, you got an undo key, and if you want to point to anything, that's a laser pointer. You can change colors here. I'd go with the highlighter and then just pick whatever color. Actually, no, follow my color scheme. So, anyway.
I just found them. I don't know where they are.
All right.
Oh, goodness.
Start with which one you think is the dimethyl tail. And I'll give you, yeah, go ahead.
The orange one.
Yep.
That's my best guess.
All right, push down a little harder so you
Oh.
can highlight. Yeah, there you go. That's better. Very good.
So then, that one.
All right, so how did you know? That's good, actually. That's really good. Yay. So tell us how did you know where to start?
This one's the pointer.
That's the pointer. Yeah, there you go.
Well, I wanted to start with that one
'Kay.
right there
Good.
being the head.
Okay.
That just seemed like it made the most
Yep,
sense to me.
dimethyls is the place to start. Good.
Yeah. And then these two connect to each other. So this is the next branching
Yep.
one. And so that one would be right next to
Good.
the tail of that one, which would create that bond.
Okay.
And then this is the next little branching area, and then that would connect for that one.
Great. Great. Excellent. You're looking for 1-5 connections, basically.
Yeah.
Very good. All right. I think we need a third round of applause. Thank you, Hank. Okay. Did anybody see an alternative? Is there an alternative way to identify isoprene units? Go ahead.
Instead of having the red go like across, could you have that red go up?
Right. Instead of so you're saying here at red 2 and this is red 4, instead of doing this, could you have also, whoops, we lost something. Could you have come up here and that's red 5 and then done this and that's blue 1, 2, 3, 4, 5. Yeah, that's also totally reasonable because it has 5-to-1 connections. So this is why I can't show you both of those options and say which one is right, because they're both right. They're both reasonable. Likely, if you chose to think about it this way and then propose a mechanism, you'd come up with a slightly different mechanism if you chose to think about it this way. What I will do instead is I'm going to choose one of these. Let's choose Hank's. I'm going to choose one of them. And then I will say you've got bonds A, B, C, D, and E, and I'll say which one of these were in the linear precursor? Which one or ones of these were in the linear precursor? Or alternatively, which ones had to have been formed? Which ones were not in the linear precursor? So the best way to deal with this is just number the carbons in your isoprene units, identify carbons 1, 2, 3, 4, and 5. Then you know that all of the 5-to-1 bonds were present in the linear precursor. That would make the other ones new, right? And maybe I need a different color than blue. Maybe the other ones were new. Now, you would come to a different conclusion if you switched up the isoprene units. For the assignment below, these are the 5-1 bonds, and these are the ones that are different, okay? So naturally, again, I have to show you the isoprene units to make this a fair question. But having shown them to you, then you can easily tell me which ones were present in the linear precursor, which ones weren't. Does that make sense? Okay. It might be useful. Let's just, for you to see, and I've got a mechanism for this cedarol written out, but it might be useful for you to just really challenge yourself and see whether you can come up with a mechanism that's reasonable. What we'll do is I'm gonna start you out here via a known intermediate, and if you go back and look at the synthesis of limonene, you will see some similarities. This is from a molecule that's 1 isoprene unit longer than limonene. But see if you can start here. Not now, but when you're studying, see if you can start here and get all the way to cedarol. And it doesn't matter to me which method you choose, whether you want to choose assigning the isoprene units this way or this way. Whatever works, but see if you can find a mechanism that works. And your focus is going to be, how do I make the purple bonds? How do I make the bonds that were present in the product but not in the starting material, using the tools that I have, which are leaving group leaves, nucleophile attacks carbocation, elimination of a beta proton, and carbocation rearrangement. See if you can come up with something. Not now, but later. And I'll write some alternatives in the notes so that you can test yourself. All right, in the last little bit, we are not done with terpenes yet, because I want to show you how this same molecule, farnesyl pyrophosphate, can be used to make a much larger molecule called linosterol. Why we care about linosterol is because it is the common precursor to all steroid hormones, to vitamin D, to cholesterol, and to bile salts. It's used a ton in nature, and it follows this pathway, which you can understand using the 4 basic terpene toolbox reactions. So the first reaction is a weird one. It's one that's catalyzed by an enzyme and requires a reducing agent, and it does not involve the 4 toolbox reactions, so we're not going to worry about it. The mechanism is pretty well known and understood, but it's sort of beyond the scope of this class. If you want to know more about it, you can come talk to me. Basically, you use a reducing agent to take 2 molecules of farnesyl pyrophosphate and to connect them head to head via a 5-to-5 bond instead of a 5-to-1 bond. Squalene is the name of this molecule. It has 6 isoprene units. On the left-hand side, you have 3 that are connected head to tail. On the right-hand side, you have 3 that are connected head to tail, but the 2 left-hand and right-hand sides are connected via a head-to-head linkage, which is weird, unusual, and it requires a reducing agent, which is NADPH. That's just a variation of NADH that has a phosphate group on it. Squalene is produced biologically. It's a lipid, and it's involved in the oils that are secreted from glands in your skin. So skin oil, a major component of that is squalene. But it has a lot of other purposes. An enzyme called squalene monoxygenase, and here I've redrawn squalene in a slightly more efficient way that's going to help us see the reactions. And I'll just say, all of this is going to be in notes that I post. You shouldn't try to copy this down because it's just too much. Squalene oxidizes just this double bond between gold 2 and 4. Squalene monoxygenase oxidizes that one as an epoxide. In the lab, you'd use MCPBA, but you would worry about the fact that you've got all these 5 other double bonds, and how are you going to just modify the one? The enzyme takes care of that by positioning this double bond and only that double bond near the oxidizing agent. So here is squalene epoxide. Now, what do you remember about epoxides from 351? Where do they open if they are protonated? On the more substituted carbon. That was a 351 thing. You learned that epoxides, if they're attacked by strong nucleophiles and they're not, and the epoxide isn't protonated, it opens at the less substituted carbon because of sterics. If it is protonated, then it starts to open before the nucleophile attacks. The mechanism is more SN1-like, and so it opens at the more substituted carbon. And that's what happens here. The epoxide gets protonated. Then the pi bond between purple 4 and 2 is ideally positioned to open that epoxide intramolecularly. The pi bond acts as a nucleophile. Now, you've never seen a pi bond act as a nucleophile to open an epoxide before, but it can in the context of the enzyme. You're going to make a new bond between purple 4 and gold 2. That's where the epoxide wants to open naturally, and we want the bond to be involved in purple 4 so that the positive charge can be on carbon 2. Now, I will point out your text does talk about this, but it talks about all these steps happening at once, because in reality in the enzyme, that's what happens. It's a cascade of a lot of steps. I'm breaking them out and showing them to you individually because individually they make sense based on the 4 terpene toolbox reactions and things you've learned about carbocations. So the intermediate you would get now has a positive charge on carbon 2, and you made a 6-membered ring. And you know 6-membered rings are reasonable and stable as intermediates. Now, lo and behold, the carbocation on purple 2 is near a pi bond that's just the right number of atoms away, such that if this pi bond attacks that carbocation and you do Markovnikov regioselectivity, you're going to get a 6-membered ring with the plus charge on the more substituted carbon. So a second pi bond attacks an electrophile. Again, everything is positioned just right so that you can get the 6-membered ring. That establishes 2 6-membered rings. The stereochemistry of the addition is controlled by the enzyme. You then have a positive charge on green carbon 2, and it is close to this pi bond between red 2 and red 4. Now, the head-to-head switch here makes it so that we've got 2 offsetting considerations. When this pi bond attacks this electrophile, if we make the more stable 6-membered ring, that would put the positive charge in the next intermediate on less substituted carbon 4. But if we make the more stable carbocation by having 4 make the bond with green 2, that's going to make a 5-membered ring, which is less stable than a 6-membered ring. So you've got one way you get a better ring but a poorer carbocation. The other way you get a poorer carbocation but a better ring. The enzyme helps control this. What ends up happening here is we make the better ring by making the new bond between red 2 and green 2, and we're going to make the less stable carbocation. That's justified perhaps because of the shape of the enzyme active site, and perhaps because all of these steps happen in close succession, so the resulting carbocation isn't around for long enough for its stability to matter. Once you have the positive charge there, we're going to have this pi bond attack here, and again, now nature wants a 5-membered ring in this position. If we make the bond between blue 4 and red 4, we have a 5-membered ring with a more substituted carbocation. And that gives you this core structure of 3 6-membered rings and a 5-membered ring in this arrangement. That core structure is universal through steroid hormones and bile salts and cholesterol. Some people call it 3 rooms in a bath. I never really thought it was that cute, but you'll occasionally hear people call it that. Now, we're not done yet. We're not even actually halfway through, because this is called a protosterol cation. Ultimately, before we can do anything else, we need to do an elimination reaction, but the place where nature wants the pi bond is actually here in a molecule called linosterol. And if you look, that pi bond is way far away from where the positive charge is. Zooming back in on the protosterol cation, if we did an elimination reaction, we could have pi bonds here or here or here, but we actually want it here. So when a pi bond, we basically need to get this positive charge from up here all the way there. What's going to happen is a crazy series of carbocation rearrangements, one after the other. And so, and if you look at the starting material and the product, you can see evidence of this in the stereochemistry of the hydrogens and the methyls that move. For example, on blue 4, you have a proton that's down. If it were to do a carbocation rearrangement, it would simply lean over and make a new bond with blue 2, but it would still be a wedge. Look at the stereochemistry of the product. I meant dash when I said wedge. It would still be a dash. It's a dash here. As it leans over, it's still going to be a dash. Look at the product. Indeed, that's where it is. Then imagine, well, actually, we'll just go through this step by step. So the proton I've highlighted in blue leans over. in a 1,2 hydride shift. That now puts a positive charge on this carbon. The proton in red from the red isoprene unit leans over, 1,2 shift. That moves the positive charge to this carbon. Methyl group in red leans over, 1,2 methyl shift. Puts it on that carbon with stereochemistry preserved. Puts the positive charge here, 1,2 methyl shift. Moves the carbocation here, and then you can finally do the elimination step to get linosterol. So if you go back and look at the stereochemistry of those 4 groups that moved over, we had 4 1,2 shifts, 2 hydride shifts, and 2 methyl shifts. And if you compare the stereochemistry of the product to the starting material, everything's still in the same place shape-wise. It's still on the same side of the molecule, but they've all just shifted over 1. It's thought that all of this happens, all the carbon-carbon bond forming steps that we talked about earlier happen in the same step, and all of these 1,2 methyl shifts, it's thought, happen afterwards, but all at the same time. I've shown it stepwise so you can see each intermediate and have an idea of what's reasonable. What your text will do is frankly somewhat frustrating, is it's going to just do this. And you might be wondering, I've never seen anything like that before, I have no idea what's going on. So that's why I've shown it out sort of stepwise for you. Interestingly, linosterol is quite different from cholesterol and from the steroid hormones and from bile salts. There's still a lot of processing that has to happen, but this is the common precursor. For cholesterol, for example, it's 19 more reactions from this to cholesterol. A lot of them are pretty complicated, involve some oxidation chemistry that we're not prepared to talk about. I just find it really interesting that if your goal is to lower the amount of cholesterol, the way that chemists and biologists have chosen to do that is to inhibit a step that's so many steps in advance, and it's just interesting that that works. So think of everywhere we've been since the beginning of last lecture when I talked about the mevalonate pathway. Can you even sort of imagine? In the mevalonate pathway, you start with acetyl-CoA, you do a Claisen reaction, then an aldol reaction, there's a decarboxylation, eventually you get to these 2. Then from those 2, you need to make geranyl pyrophosphate, which was what we learned from our toolbox of terpene reactions. From geranyl pyrophosphate, you need to tack on a 3rd isoprene unit to get farnesyl pyrophosphate. Once you've done that, you got to link the 2 of them together to make squalene, then you got to make the epoxide, then you got to open up the epoxide end, boom, 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 close the 4 rings, then boom, 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 carbocation rearrangement, elimination, linosterol, and then you're still not to cholesterol. So the statin drugs inhibit something very, very early, but it's really effective at lowering your cholesterol. You might want to ask, well, what about the other steroid hormones and bile salts? Do those get suppressed with statin drugs as well? I don't know. That's an interesting question. We ought to look it up and see whether some of the side effects of statin drugs are related to those things. All right, with that, that is the end of chapter 25. So we will move on Monday to nucleic acids, chapter 26.